Hi, good morning, and welcome to the FoodSense webinar. So we like to do this webinar once a week, and really we're just answering technical questions that have come in during the week. So I'm going to dive straight into it and just say that this week we're talking about measuring chili powder. I am going to talk about heterogeneity of chili powder and how that in a chili powder sample you have to do multiple tests in order to understand the heat or the Scoville Heat Unit of the entire batch. So I think one of the big problems that happens is that people take a single sample and they send it for HPLC, high pressure liquid chromatography analysis, and they get a single result back with no error, and that's held as the sort of absolute truth. And I want to sort of pick that apart a little bit today. So let me dive into it and say that the problem that we're solving with FoodSense, especially FoodSense Generation 4, is that, these are some old slides, but I'm gonna sort of re-talk about actually the problem that we are solving, which is if you want to know the hotness of a chili sample, you're basically trying to measure the capsaicin, and the analytical methods are the kind of HPLC method, panel testing, guessing, and FoodSense. Now, the big issue with the industry at the moment is actually on the analytical testing front with this HPLC because of its expense, and you'll see this today in a case study where there's 4 HPLC results and 19 FoodSense Generation 4 results, and that really fundamentally reflects the expense of actually doing HPLC testing. Because of the expense, then it leads to what's called under-testing. So under-testing just means one sample goes to the lab, a certificate of analysis comes back, and that is held as the truth. But it's really an under-tested sample. What you'll see in the results today is if you do something like 5 tests, you will get 5 results, and it reflects the heterogeneity of the chili sample. So under-testing is a problem. Slow results is a problem. I suspect that people take samples, they get packaged up, they go to the lab. The lab waits till they got enough samples, then they do a run on the chili samples, and then you get the results back. And then it's this, I would actually describe it as the current system is a bit of a black box with no sense of error. So what I mean by that is you kind of post that package off, you get the result back, and you just assume that everything is great. And I want to pick that apart a little bit today as well. So I am going to talk about FoodSense, and I am going to sort of say, well, look, depending on where you are in the world, FoodSense as a technology actually costs less than 1/50th the price of a HPLC system. The reason that most of this testing gets done externally is because HPLC is so expensive to buy, expensive to run, and so that people are essentially are outsourcing this. But that outsourcing could also be a bit of a problem. Because now you can own the instrument, there's a lot more testing going on. So you'll see today in the case study, and these guys are doing some good science here, that they've tested 19 times on the FoodSense, but as I say, only 4 times on the HPLC. So they're now able to do a lot more testing, which means I can actually do a lot more statistics. I can't do statistics when somebody's only got 1 HPLC result, but we can do it now because these guys are doing a lot of testing. Fast results, essentially there's no admin sending off to a lab, but also I would also say there's a security on the results. And what I mean by that is it doesn't, happen so much probably, but if you send a sample to the lab, who's not to say that it didn't actually get mixed and the results you got back were somebody else's results? That can happen. I mean, it happens in hospitals and it can happen in analytical facilities as well. They try to minimize it, but it does happen. So not only do you have fast results with FoodSense, but you also have security on the results because you're the one who did the test. And also, FoodSense is a very transparent process. I'm going to show you today that when with the HPLC, there is no access to the raw signal and there's no access to understanding the error in the methodology. But with us, there definitely is a transparency that I am able to look at their raw signal and say, the number you're getting on the machine is exactly what the capsaicin concentration is. So I am really talking about the SensiAll platform. SensiAll has kind of, we're bringing in optical measurements. These are for different analytes, but at the moment today I'm talking really about FoodSense Generation 4, this piece of hardware here. If you're so interested, I've got a QR code up here which is about the software, but you do need the hardware in order to run this. This webinar is really about the support that we give people. So we do have, everyone gets personalized online training. We do have weekly webinars. This is that weekly webinar. And we do have monthly webinars. So tomorrow there is a webinar with a live demonstration. So if you're a FoodSense Generation 4 user, we're definitely here to help. It's much easier to help the FoodSense Generation 4 guys. And if you've got come to the webinar tomorrow if you can. But if you've got an analyzer application that we're not covering with FoodSense, but maybe is linked to the ingredients part of the supply chain, we'd be interested in hearing about it. This is the webinar tomorrow on the 14th of December. I'll try to remember to put the links underneath the video after this has gone live, and I will plow forward. So they're concerned about the Scoville Heat Unit results. When they say you hear fluctuation suggests up and down. I'm not sure that they really mean up and down, but they were, because it says here it's fluctuating much higher than the HPLC results. But when you've only got one HPLC result, you don't really know what the fluctuation on the HPLC results really is, because you've only got one result. But I'll look at your data and discuss your data. The background to all of this is that chilies and chili powders in particular are heterogeneous samples, and you get what's called sample-induced errors. And I'm going to explain what I mean by that. So if it was homogeneous, you could sample anywhere and you would probably get an accurate result. But when you've got a heterogeneous sample, you've got different amounts of capsaicin throughout the sample. If you sample in one place, you'll get one result. If you sample in another place, you get another result. This is the problem with chili powders, and that's why you need to have a higher number of tests. But nobody does a higher number of tests because they're too expensive to run by HPLC, and that's where the FoodSense kind of kicks in. So the discussion in part today will be about heterogeneous samples, chilies and chili powders. And I'm not going to talk so much about homogeneous mixtures, but by the time you've blended this stuff up and put it in vinegars and oils, then it's much easier to get a representative sample because everything is homogeneous. So on one side of it, you've got sort of chili purees almost here, and on the other side you've got heterogeneous complex samples. So I'm talking more about heterogeneous complex samples today. I mean, it all starts off in the fact that if you slice open a chili and analyze the parts of the chili, what you're going to find out is that most of the heat is actually in the ovary. I know that professionals like I'm dealing with at the moment know it's not in the seeds, but people have this perception more generally in the general public that actually it's in the seeds, but it's actually in the ovary. But this is the start of the sample-induced error issue, that actually in the chili itself, the capsaicin is not throughout the fruit. It's actually concentrated in the middle of the white material, and not in the seeds as some people think. When you dry it, you don't. All you do really is end up concentrating that that hotness rather. I mean, the nice thing about the FoodSense is we're able to follow processes. So if you follow a wet fruit, you may find that it's got a overall Scoville Heat Unit of sort of 4,300, but by the time you dry it and you intensify it, then you're getting more to like the 50,000 Scoville Heat Units. And that's because 90% of a chili is actually water. So the reason I'll back up slightly and say, right, so today I am dealing with chili powders, but I want to say that the big problem that happens is that people are not doing enough testing on the HPLC results, and they're not challenging it enough, and they're not doing enough testing because it's fundamentally a problem of expense and time. But if you have a very heterogeneous sample, and I sample here, then I essentially miss the capsaicin. If I sample here, I miss the capsaicin, and if I sample here, I hit the capsaicin, and if I sample here, I hit 2 capsaicins. If I make this a bit more of a blend and break up that capsaicin a bit, and I sample here, I get capsaicin 1, here I get about 3, here I get about 2, and here I get about 3. So I'm showing you that by going from a very heterogeneous sample to a bit less of a heterogeneous sample, and then if I go to a more homogeneous sample, if I sample here, I hit about 13. If I sample here, I hit about 13, and I sample here and I hit about 13. So this tells you that if you're trying to sample on Tabasco sauce, for example, then it doesn't matter where you sample, the whole thing is quite homogeneous. But when you are dealing with chili powders, it actually becomes more important that one sample is not going to be representative of the entire chili powder, and I think this is at the heart of what's happening. With chilies, it's even more extreme, that you have to really chop it up and blend it and essentially reduce it to a powder in order to kind of get somewhat of a homogeneous sample. So chilies I would describe as highly heterogeneous, and powders I would definitely describe as heterogeneous. And on the very extreme, I think the most pureed, mashed up material is probably Tabasco sauce, which is not today's talk. But just out of interest, if I do the statistics on this, that I've sampled here, I get 0, sample here, I get 0, sample here, I get 1, sample here, I get 2, then my relative standard deviation is 141%. That means that essentially I've got a spread in my data of 141%. With a chili powder, if I sample here, I get 1. If I sample here, I get 3. If I sample here, I get 2. If I sample here, I get 3. I get a relative standard deviation of 43%. I think this is starting to represent what's actually happening in a chili powder. That you will take a sample, you send it to the lab, you get an absolute result. And I'm sure that absolute result is somewhat reflective of that sample, but it's no reflection on the entire batch of chili powder that you're actually dealing with. And if I deal with a chili sauce, doesn't really matter where I sample, I get 13, 12, 11, 10. My error is coming down because, in fact, the sample is so homogeneous. And I have done a look at that, actually, chilies. This is my own work. This is chili powder under the microscope. And you can see by looking under the microscope that the particulates are actually different sizes. They're different colors. Color's not necessarily a reflection of capsaicin, but it is a reflection that chili powders are not homogeneous samples. They're actually heterogeneous samples, and you don't have to put them under a very high-powered microscope to see that. So those are images that I've just recently demonstrated. So what I'm saying is that people will get HPLC results, and they'll get an absolute value, and they'll take them as as the truth. But I'm saying that if you sample, let's say 5 times from a chili powder, then you will end up getting 5 different results. Now, what you really need to do to understand the average or the mean Scoville Heat Unit of that sample is you need to send it off to the lab, 5 samples off to the lab. But people don't do it. But with the FoodSense, they are now able to do it. And you'll see that in the data today, because now they can actually do a low-cost rapid test, whereas they can't do it on the HPLC. And the reason being is what I said before, that HPLC is expensive to own, so you don't own it, you outsource it. Therefore, because it's expensive to get the test done, you're under-testing. You'll only do one test. The results are slow. And I'd also describe this as a black box with no sense of error. What I mean by that is you put something in the mail, you get a result back, but you've really no visibility on actually what's happening with that sample along the way. Whereas obviously with the FoodSense, there's it's much lower cost, so people can actually own it. Therefore, they can do a lot more testing. They get faster results, and they also, it's a transparent process that they get a result there and then. They're also able to look at their raw data, or they're able to share their raw data with us, and we can actually look at their raw data. So when I say HPLC is a bit of a black box, I mean, you've got a sample of chili powder. You take potentially 1 sample from that chili powder, and you send that off to the lab, and they do an extraction on it. They may do a filtration, by the way, but they definitely do a dilution. And then they do an injection onto a column, and then they actually get a chromatogram as the capsaicin essentially leaves the column, and they get essentially a raw signal, which is this chromatogram. Then, at some point, they've done a calibration, but they've not necessarily done a calibration on that day. They may do the calibrations weekly, because calibration is going to be time consuming for these guys. So then they do a calibration. So they turn the raw signal back into Scoville Heat Units. So there I've described that there's 1, 2, 3, 4, 5 processes. Now each process will have an error associated with it. So if I just assume, this is a high assumption that there's 5% error, I'll end up with an overall error on this system of 25%. But when you actually get your results back, you'll have no indication of error associated with that test. You'll just get an absolute number. What you really need to do, and nobody does this, and nobody does it because it's too expensive to do, is actually, if you took a sample and sent it to lab 1, you'd get a certificate of analysis. If you took a sample and sent it to lab 2, you'd get a certificate of analysis. And if you took a sample and sent it to lab 3, you get a certificate of analysis. None of those 3 results will be the same. So the problem with that you've got sometimes with these HPLC certificates of analysis is you get a number, you say that's the truth, But actually, if you sent the same sample to a different lab, you would get a different result. So you can't hold it as the absolute truth. In fact, none of them would be coincidental. A side note here: if you took the same sample, sent it to the same lab 1 month, you sent the same sample to the same lab another month, but give it a different name, and you took the same sample, you sent it to a different lab the same lab on a different month. So I'm basically sending the same sample 3 times to the same lab, but you have to blind the lab. You have to give the lab different names so they don't realize that you're sending the same sample. You will get 3 different results. So that these absolute accuracy on an assumption of precision on HPLC testing is an assumption. It's not actually the case. So you will end up with, if you send the same sample to the same lab but separate it in time and give them different names, you will get 3 different results back. So when you look at a certificate analysis, I mean, this is just what I found on the internet, but I've seen this before, that this is a heterogeneous sample. These are dried chili, so it's definitely heterogeneous. They've run an HPLC method, this AOAC 995.03, so I get that. And they've got the results quite low, actually. It's 11,636, but maybe that's correct. But what's interesting is there is absolutely no uncertainty indicated. So this is a multi-step process involving the conversion of a chromatogram, essentially raw signal, via a calibration routine to a Scoville Heat Unit. But you have no indication of error here. And when we look at the results I get today, there's no indication of the error associated with that result. I just want to say hi to Aftab. Aftab supports, he's online at the moment. Aftab supports the FoodSense in India. So when I look at all the raw data today, Aftab has been supporting that. He's also the CEO of Technando. So my point here is that HPLC results are a multi-step process. Each step in that process will have an error associated with it. And so when you get this absolute value of like 11,636, you should actually have an error associated with it, but there's no indication of error. So people take it as absolute, the truth. Now the background to this is, the only reason I bring the background up of this is because today I'm going to be showing you raw signals from the FoodSense Generation 4 product. And the only reason being is that I bring this up is because this technology originally started at the University of Oxford with a guy called Professor Richard Compton. I think he's at St John's College in Oxford. And he came up with a method for analysing capsaicin. So both HPLC and FoodSense Gen 4, in the end, we're both trying to get to the capsaicin concentration. And the only reason I bring this technique up, this is a voltammetry technique, because you'll see a lot of voltammetry today. Now, the user experience is you put the sample on the sensor, you'll actually get a Scoville Heat Unit. But understand that there's a higher level of transparency in the food sensor. Actually, the raw signal is going to the cloud. And Aftab, for example, and the clients that I'm dealing with in India, they're actually able to share that data with me. So what's happening is, these CVs that you'll see today, the CVs are actually showing me the electrochemical activity of capsaicin. So there's very distinctive peaks in the CV. So the first peak is the oxidation of capsaicin by electrochemistry, and I get this peak. And then there's another peak then that appears. This is out of Richard Compton's original paper. There's another peak then that appears here, which is the reduction of the molecule. So now I can see that the molecule is reducing, and it's very distinctive because on the what we call the second scan, there's a new peak. So that peak wasn't on the first scan, and then the second peak actually, or the first peak here, diminishes. So there's a very distinctive fingerprint, and you're going to see that today in our data. So the positions of these peaks and their intensity tells me that A, it's capsaicin, and B, how much capsaicin is in there. The reason I bring this up is because when you get these HPLC results, you have no vision on the chromatogram, and you have no vision on actually how they went from chromatogram to your Scoville Heat Unit. So the nice thing about what we're doing is there's actually a transparency to this. So let's talk about the case study itself. So here we're dealing with about a series of 19 tests. There's 2 columns here. This F-lab results, I believe, are HPLC results, and these ZP kit are the FoodSense Generation 4 results. So they have HPLC and they have FoodSense Generation 4. And they're a bit concerned about the correlation between HPLC and FoodSense. The first thing to note is on the HPLC results, when you look at the column, these two numbers are the same. So this is not repeat testings. This is just one test. So they've tested once by HPLC, they've tested twice by HPLC, they've tested 3 times, and then this is the 4th. So they and it's no criticism, it's due to the cost that they've got 4 HPLC results. Yet when you look at the FoodSense, they've actually got 19 results, and this is getting to the heart of what FoodSense is, which is, you know, a rapid test system that they can actually own themselves, as opposed to shipping it out to a third party. So they want to understand. They want us to look at their results and comment on their results. So that's what I'm going to do now for the rest of this webinar. So the first thing to say is that they have something called R chilli and S chilli. Now, what I notice is, if we look at the results a bit closer, I'm able to look at the HPLC results. So here I can see their R chilli, and here I can see their S chilli. The first thing that, and I can also see the peak heights. So it's not lost on me that R chilli is, according to the FoodSense, is 112,000 Scoville Heat Units. I can see the raw signal here. It says 2.41. If I look at the S chilli, the FoodSense says it's 71,000 Scoville Heat Units. If I look at the raw signal, I can see it's actually 1.563. That signal is bigger than that, and that's why that number is bigger than that. So what I'm saying is I have a transparency on this. I'm able to look at your raw signals, because even though these results are being gathered in India, every time they do a test, the test goes up to the cloud and it's saved. And then they have chosen to share the raw data with me. That's really important that you understand that they've shared the raw data with me. So now when I look at that result, I can look at the raw signal and say that is high, and that's why that number is high. I can't comment on the HPLC result being 65,000. What I can comment is, if you sent the same sample again and again and again, you would get different results. But I can't comment because I didn't do the work. But what I can comment on, obviously, is that on one of the tests for the S powder is, according to the FoodSense, less hot than the R powder. And I can see it in the raw signals, and it correlates very well with the F lab. So at this point, I'm able to demonstrate to you that these numbers are not just coming out of nowhere. There's actually raw signal behind this. And I'm glad that we correlate with the lab on one of the tests, but I can't comment where they're underscoring on the other test. Now, what I'm going to also, so, you know, I've looked at the raw signals, and I believe our raw signals, they're very healthy, by the way. You know, you can definitely see the peaks that we're expecting. So these, you know, this is working, let's say, just the way Oxford said. Sometimes there's things like same sample use. So this is a little bit confusing to me because I don't get many notes. I've got to, if I understand that, then I can probably comment a little bit more on this. But this is really, in that whole table, they had sequence 3 and 4. They had a result for sequence 3 and 4, and it's kind of interesting because 77,000 is similar to 73,000, but that 124,000. But I will look at the raw signals. But I need to understand that they've done the dilution correctly. But I need to understand this word direct, you know, direct 1/100 dilution, 1 in 100 dilution through 1 mil. I need to understand what that means, because when I understand what that means, then I can understand what's actually going on here. But I don't have that understanding. So I do need to understand those subtleties, because there's something subtle between these two. So when you do one process, it's higher than the HPLC, and when you do the other process, it correlates well with the HPLC. But again, we can look at the raw signals. So when I look at that 124,000 Scoville Heat Unit signal, I can see it's high. And when I look at the 73,000, I can see that this is getting close to 10 here, and this is actually more closer to 5. So I can definitely see the raw signal is telling me that this is telling me that it's capsaicin, and the peak intensities are telling me how much there is. There is more here than there is here. There's simply no doubt about it. But if I understand those words, I basically need more details, and I finish my presentation with that as well. Then I can explain to you why. But the raw signals are telling the story. This is the best set of data that we have. And it's because at this point now, we actually get powder 1, 2, 3, and 4. We're starting to get statistical and statistical sort of numbers on this, that there's been 5 tests performed. Now, this same sample used is again a little bit confusing for me. I have to understand what that really means. Is it the same sample tested 5 times, or is it the same sample sampled 5 times and then tested? So when I look at their results, what I think we're looking at here is one sample, but then they've sampled it 5 times. So I think it's like, and then they've made up these 5 solutions. So we've got sample 1 from the sample here, sampling 1 from the sample here, sampling 2 from the sample, sampling 3, 4, and 5. So then when they get the results, what they end up with is 5 different results, but that's actually reflecting the heterogeneity of the sample. What they need to do then is actually test it 5 times by HPLC, but they can't do it because it's too expensive. When I look at their results, then we actually end up with quite interesting that we got 1 high, 1 low, and 3 in the middle. This is very common when you've got a heterogeneous sample. What you have is what's called a normal distribution. You've got low, then 3 in the middle, and then 1 at the end. That's basically tracing out what's called a bell curve or a normal distribution curve. And the mean of that is 76,000 with a standard deviation of about 13,000 and a coefficient of variation of about 18%, which I think is not bad actually for a heterogeneous sample. And so we have essentially a mean of 76,000, a plus or minus 13,000. But what's interesting is, on your HPLC result, you get this absolute number. So you're comparing 65,000 versus 76,000, which is not so dissimilar actually. But you've no idea on the error of that 65,000, because if you know what the error is, you can then do a t-test and ask, in the t-test, you ask the question, is this number different from this number? This number has an error, this has a number. So taking account of these errors, are they actually the same number or different numbers? So you can do a t-test, which is a statistical analysis. I just realized something actually. The t-test was invented at Guinness in the beverage industry, and was actually sort of invented for this kind of application, where you're testing kind of complex matrices. So you would say, oh, those numbers are different, but actually you can't say those numbers are different because you don't have the error associated with the HPLC, and if you did, then you could do a t-test. So I actually suggest that they're actually quite similar, the two numbers. But this is the power of the FoodSense, that they were actually able to do 5 tests here and only 1 test here. So now this person can actually say, okay, so I have a result of 76,000, but I have a plus or minus 18% on that. On the HPLC result, they just have this absolute number, no idea of error, and they just take it as an absolute number with no error. And again, there's 2 ways you can test this. You can actually send the same result to different labs, and you get 3 different results. And if you send the same sample to the same lab over 3 months, you'll find that you get 3 different results. Now I'm going to go through all of their data. So what I notice here is on this MP test, the Scoville Heat Unit gave it 57, the HPLC gave it 76. I can't comment because if you did it multiple tests, then what we're going to end up with is because it's a heterogeneous sample, we're going to end up with some 1 low, 1 high, and 1 in the middle, and then we'll be able to compare it against that 76,000. But I find it interesting because when you look at this table, there's a TB result here, a TB result here, a TB result here, a TB result here. So now I can do some statistics and some analysis on that. So I'm going to look at those TB results and say, what I can say about the MP results actually is that on the MP result we say it's 57,000. I mean, I've checked the raw data. To be frank, it looks really good. You can see the peaks; they're all healthy. And I can see the intensity, so it does look about 57,000. Again, you are assuming that HPLC result is absolutely accurate. That is an assumption because it's basically a black box to us what's actually happening. I understand it, you understand it, but neither of us is necessarily in the lab seeing it happen. Let's look at the TB results. So the TB results are actually really interesting because, again, I don't really have enough data. I'm only using the names, but you've got TB, TB, TB. So I got 177,000, 166,000, 142,000, 197,000. if I do the statistics on that, therefore just do the mean, the standard deviation, and then for the coefficient of variance, which is just standard deviation divided by mean, and turn it into a percentage, it's 13%. It's really close to what you actually had on those, I think it was S samples earlier on, of 18%. Now, it's not the same number as your HPLC result, but when I look at the raw signal, it's huge. It's huge, okay? I'm telling you that the raw signal tells me it's huge. So it's not just this number's coming from nowhere. It's huge, and you did it 4 times approximately. So I'm sorry, but the body of data is actually is in support of the FoodSense, because the raw data shows you can go through the slides and you can see that these numbers, none of these peaks are like this. These are huge. So by far, the TB is by far your hottest product, because I can see it in the raw signal. So when you get this kind of 84,000 from the HPLC, you've no transparency on that. What was interesting is when I was talking to this team, I think the head scientist said, I'm not so interested in absolute values. I'm actually just interested in being consistent. You are being consistent when you do when you do FoodSense results. You are being consistent. You've had, as let's say, a standard deviation or coefficient of variance, of 18% on one of the tests, 13% on the other one, and it's super interesting. And like I say, the raw data is backing up that number is huge. I just want to say, lastly, you've got some more results, but you've no HPLC, so I can't really comment upon it. But I did find it interesting that you've got a chili powder A part A and an A chili powder part B. I don't know the history on these samples, but I don't know enough. But if I did a statistical analysis on them, they're actually, the error there is more like a 6%. So, it's sort of, your precision is good, I would say. Your comparison with HPLC, you're doubting it. But I would actually say the strongest case is probably on that TB, where you kind of say, well, the FoodSense says it's very hot. The HPLC says it's only 84. Sorry, there's one sample, there's the other one. It's huge numbers. So I suspect that the HPLC you're blinded on, and you don't and you've no sense of error on that HPLC result, let's say. But your testing is actually starting to be really quite consistent on the FoodSense. So my comment is this, that at ZP, we will support FoodSense Generation 4 customers to do this work. I think I've worked on and off this now for 4 days, because there's quite a lot of data to go through, a lot of analysis, and a lot of looking at the raw signals. We are able to back up our numbers. So the user experiences, they just get the result on the phone. But actually, thanks to TechNando and thanks to the team who is using this system in India, we actually have the raw signals. So we're able to back up our numbers with the raw signals. What if you want ZP to support you, what will happen then, what will be useful then, is to have details. Because there are interesting comments like direct 1/100 dilution through 1 milliliter. I need to understand those comments, because then we can actually figure out why that one's high, that one's exactly in line with HPLC. But I do find it super interesting that one thing I would notice is I think that we're correlating well with HPLC. We're not agreeing absolutely on the values, but I can then go back and verify your FoodSense Gen 4 results, because I can look at the raw data, but I can't do the same on HPLC, because those chromatograms and that calibration data is not available to you either. If you give us the details about what you're actually doing, then I call that metadata. Then we can look at the data versus the real details that you give us, and then we can actually really kind of help. So what do I say here then? That if you're a FoodSense Gen 4 customer, it's really good, because even if you're in India, all your results in real time go to the cloud, and then if you're working with TechNando, they can actually help us access that data. And if you have tests that are not currently on the FoodSense, then we'd be interested to hear them, so we can help integrate it. So in summary, be super careful with HPLC results, because it's mostly a black box. And what I mean by that is you send results to a lab, you get a certificate of analysis back. You have no indication of the error associated with that analysis. Whereas with FoodSense, it's transparent. We can actually see the raw signals, and we can back up our statements with the raw signal. So I think in summary, I want to say thank you, special thank you to the guys in India. when you start doing the multiple testing and we start getting the statistics, that's really useful. And you're showing some really good consistency in that testing as well. So the precision is good. I also just want a special thank you to Technanda that distributes FoodSense in G4. That team is extremely IT strong, which is really useful because what we're talking about in FoodSense G4 is really a digitization and a traceability into the food ingredients market. And at the moment, that kind of digitization and traceability is not super high. But with FoodSense, there is actually now every sample is saved, so we can both the data is digitized and it's traceable as well. We can actually get back to the raw signal really quickly. So I want to say thank you with that. If you've got any questions, don't hesitate to reach out to us. As you can see that we've put in some good hours actually analyzing this data, and I hope that's useful to people. Okay, thanks very much.